In this video, we'll begin our journey into tree-based methods for supervised learning tasks. Trees represent a fairly different class of methods than what we've seen before, and as we'll see, they form the basis for some powerful statistical learning methods. You've very likely encountered decision trees before in the form of flowcharts or infographics. Take, for example, this snippet of a decision tree to help gamers decide what video game to play next. The use of a decision tree is fairly intuitive. We start at the top of the tree and follow the paths corresponding to answers to the questions posed in the rectangles. Ultimately, the final node we reach is our game recommendation. Thinking about how this chart was likely built actually helps motivate the ideas for how decision trees are constructed. The intuition is that a large number of gamers, the cases in the dataset underlying this graphic, provided information about the questions posed in the rectangles, the variables in our dataset, as well as on their favorite video games, the outcome variable. Based on this information, the chart designers were able to find series of questions, sequences of variable characteristics, that would divide gamers into subgroups with fairly uniform preferences in video games. This is exactly the intuition behind the building of decision trees. Let's unpack this. In general, the strategy that decision trees make for making predictions is to continuously split the data into data subsets, also called regions, data subsets based on the predictor values, until the outcomes are fairly uniform in that region. By fairly uniform outcomes, we mean that within that subgroup, all or the vast majority of cases have the same outcome. As an example, we'll look at a dataset that allows us to understand predictors of heart disease. Our goal is to predict heart disease from other clinical characteristics. The bar plot shown here shows how the conditional probability of having heart disease, the blue portions, changes based on the outcome of a clinical test called a thallium stress test. We see that a normal result on this test is associated with a much lower chance of heart disease than a result of fixed or reversible. So we might imagine that splitting the data into those with normal and non-normal results is sensible for predicting heart disease. A decision tree using just this variable is probably too simplistic, but let's look at the resulting tree to define some terms and motivate ideas. Each junction in the tree corresponds to a statement about a predictor that can be described as splitting the data into subsets. We see that the thallium stress test predictor is considered at the tree's only junction, and the data is split based on whether the result is normal or not. If yes, then we follow the branch to the left. If no, we follow to the right. Each rounded rectangle is called a node, and the nodes at the very end are called leaves. Each node has 3 lines of text. The first line is the predicted class at that point in the tree. The second line is the predicted probability of the y=1 event at that node. The last line is the percent of the training cases present at this node. The topmost node, also called the root node, summarizes the data before any splitting, which is why 100% of the training cases are present at this node. The predicted class at the top of the node is no heart disease because the majority of the cases, 160 out of 297, don't have heart disease. In general, the predicted class at any node is a majority classifier. The class that forms the majority is the predicted class. Following the split to the left, 55% of the cases have a normal result on the thallium stress test, and to the right, 45% of cases have a non-normal result. The 0.23 on the left leaf indicates that among the 55% of cases who have a normal stress test result, only 23% have heart disease. Since the majority of cases at this node, in this data subset or region, don't have heart disease, the predicted class is no. The 0.75 on the right leaf indicates that among the 45% of cases who have a non-normal stress test result, 75% have heart disease. Since the majority of cases at this node have heart disease, the predicted class is yes. A full tree grown from all predictors is shown here. Let's go over some key features. First, Although it's only labeled for the first split, we always go left when the condition at the branching point is true, and we go right if the condition is false. The language that we'll use going forward is that these splits define regions of the predictor space. Predictor space is a term that describes all combinations of predictor values, and regions describe particular combinations of predictor values. Second, a predictor can be used multiple times in the tree. The CA and the chest pain variables are both used twice in the tree. This just means that once the data were split in a particular way, these variables ended up being useful splitting criteria again. Note that for quantitative variables like CA, the split is determined by being above or below a single threshold. For chest pain, if the chest pain variable is one of non-anginal, non-typical, or typical, the condition is true. Third, notice that when we follow a split to the left and right, the resulting regions are more homogeneous in the classes represented than the original regions before the split. This homogeneity is also called node purity, and it's numerically manifested by the predicted probabilities of a heart disease, which are the second lines of the nodes, getting closer to either 0 or 1. For example, for this split on the left, the original region had 49% of cases with heart disease, barely forming the minority, which resulted in an overall class prediction of no heart disease for this original region. But after the split, we see that the left region became even more homogeneous. The reduction of 49% of cases with heart disease to 24% indicates increasing homogeneity defined by the no heart disease outcome. As another example, for this split on the right, the original region had 89% of cases with heart disease, a clear majority, giving rise to the overall class prediction of yes, heart disease. After the split, the right region becomes even more uniform, with 97% of cases with heart disease. Again, this increasing homogeneity is the idea of increasing node purity, and it's a key idea underlying how these decision trees are constructed. In order to fully understand how decision trees make their splits, we need to formalize the idea of node purity. We'll use a measure called the Genie Index for measuring node purity, which is not to be confused with the economic measure of income inequality. So let P hat RK denote the proportion of training cases in region R that belong to class K, and say that there are big K total classes. The Genie Index or Genie impurity measure is defined as the summation shown here. The key idea is that we can interpret the Genie Index as a measure of node impurity. It takes a small value when a region is pure, and a region is pure when almost all cases in that region belong to one class. And the Genie Index takes a large value when a region is impure, when a region has many cases of different classes. Let's look at numerical examples to understand the Genie Index. The CA variable gives the number of major vessels visible through calcium imaging. Say that I consider splitting my data based on a threshold of 2 for this variable. I end up with 4 cases with heart disease in the right region and 2 of each class in the left region. Just by visual inspection, we can see that the right region is more pure than the left region. Let's verify this intuition by applying the Genie Index formula. We first need the outcome probabilities in both regions. In the left region, half the cases have heart disease and half don't. In the right region, all of the cases have heart disease. Based on these probabilities, the Genie Index for the left region is 0.5 and it's 0 for the right region. The left region is more impure than the right region. It has a higher Genie Index. Impurity in a tree region is undesirable because it makes the prediction in that region more uncertain. For a case with less than 2 visible vessels, it's a 50-50 as to whether they have heart disease. On the other hand, for cases with at least 2 visible major vessels, it's entirely certain, at least in the training data, that the individual has heart disease. The goal of using the Genie Index is to guide tree building. We want to use this measure to compare all of the possible splits that could be made. The overall quality of this split, vessels less than 2, can be captured by a weighted average of the impurity of these two regions. The weight given to a region is the number of cases in that region divided by the total number of cases in both regions, in both the left and right regions. So here, the overall quality of this split is 0.25. This number isn't super helpful on its own. Our question is, could another split have given us a lower number, indicating overall lower impurity? If we use a threshold of 1 heart disease case is moved to the right region. In the right region, the proportions of heart disease and no heart disease are still 1 and 0, so the Genie index for this region is still 0. But the Genie index for the left region has gone down from 0.5 to 0.44. This new split has lowered the weighted average Genie index to 0.167 from 0.25 before. So overall, this split gives regions that are more pure, which is preferable in building the tree. Now we can dive into fuller detail about how trees decide on good predictor splits. And the algorithm used is called recursive binary splitting, and it proceeds as follows. First, we search through all predictors and all of their possible split points. We find the particular predictor and split point on that predictor that gives us the lowest weighted average Genie index. This gives us two regions. And we repeat this process for each of these two new regions. That is, for each of these regions, in which a certain subset of the cases is filtered through, we again find the best predictor and split point. This process is repeated over and over to continually split the data into more pure subsets according to the weighted average Genie index. We stop the splitting once a stopping criterion has been reached. Examples of stopping criteria are to stop once all the leaves have less than a certain number of cases, or stopping once a region has been split too many times, or when there's no possible split that can lower a node's Genie index. Recursive binary splitting can be described as a top-down, greedy approach. The top-down part comes from the fact that we start at the top of the tree with all of the data in one group and split the data into subgroups as we move down the tree. This is in contrast to a bottom-up approach, in which each case would be in its own region, and we fuse the regions together to build the tree. Recursive binary splitting is greedy in that at each step of tree building, we make the best split at that particular moment, the one that minimizes the average Genie index right now. However, there very well could have been another split that would result in an even better tree in a later step. These possibilities aren't considered because many more combinations would have to be explored. Instead of just checking all possible splits of all predictors, we would have to check sequences of splits. Because the number of possibilities for split sequences grows exponentially, this would be extremely computationally intensive. So far, we've talked about trees used for classification. These are called classification trees. Trees can also be used for regression tasks, for predicting quantitative outcomes, and these are called regression trees. We'll end this video with a short discussion of how regression trees are built. In building regression trees, nearly all the ideas from building classification trees still apply. Trees are still built using recursive binary splitting to iteratively split the data into increasingly pure regions. The first point of difference is how a prediction for a region is made. With classification trees, the prediction for a region is the majority class. With the regression trees, the prediction is the mean of the outcomes for the cases in that region. The second point of difference is how region impurity is measured. For classification, we can use the Genie index. For regression, we use the sum of squared residuals. A residual is defined in the usual way, observed value for the outcome minus predicted, where the predicted outcome for each case is the mean outcome in that case's region, as we just noted. We sum these squared residuals over all cases in the region being split. So, In summary, we've learned that decision trees are an interpretable means of performing classification and regression that work by iteratively splitting the data using predictor values. Trees are built with recursive binary splitting, which is a top down, greedy approach, which is faster than considering all possible sequences of splits, but it won't necessarily give us the overall best tree. The metric used to judge the quality of a split in a classification setting is the Genie Index, which gives a measure of node impurity, or lack of class homogeneity within a leaf. The sum of squared residuals serves that role in a regression setting. One last note is that there is actually a great risk of overfitting when we build trees with too many splits. In class, we'll explore the idea of tree pruning, which can help fight overfitting. We'll also soon explore extensions of decision trees that use many trees and which can greatly increase the predictive power of tree models.